Every time you look at a camera, it's not just seeing you. It's measuring your face to guess your emotions. That smile you just made. AI already turned it into data, compared it to millions of faces, and predicted your emotion. AI doesn't understand feelings. It tracks angles, distances, and tiny muscle shifts, then guesses what emotion matches the math. The spark of intelligence. For decades, computer scientists dreamed of creating not just tools, but collaborators, machines that could understand, reason, and create. This field, artificial intelligence, moved from logic-based rules to a more profound idea: what if machines could learn from experience, just like a child? The hungry appetite. The first attempts at machine learning revealed a brutal truth. This kind of intelligence isn't born from elegant code alone. It is forged in fire, the fire of raw, relentless computation. Every lesson for an AI involves performing billions, then trillions, of mathematical operations. The dream had a ravenous, unsatiated hunger for compute. The basic unit, the faithful clerk. Our story's initial hero is the central processing unit, CPU, the brain of every general-purpose computer. It's like a brilliant, swift clerk who tackles tasks one after another with precision. But teaching an AI is not a single-file task. It's like trying to survey an entire landscape at once. The clerk, for all its strengths, is overwhelmed by the scale. The game changer, the army of specialists enter the graphics processing unit, GPU. Its original purpose was humble: to calculate the color and position of millions of pixels on a screen 60 times a second for video games. To do this, it was built not as one powerful clerk, but as a vast army of thousands of smaller, simpler workers. They all perform the same type of calculation, matrix multiplication, simultaneously. AI researchers had a eureka moment. The math of rendering a 3D world is fundamentally similar to the math of adjusting a neural network. The perfect tool was hiding in plain sight. The birth of a model. Imagine we want to create an AI that recognizes a cat. We start with a digital scaffold, a neural network, a simplified, mathematical mimic of a brain's connections. It begins ignorant. Its millions, or billions, of internal dials, called parameters, are set randomly. Show it a picture, and it guesses wildly: dog, truck, cloud. The training grind, the impossible task. The AI learns by trial and error. Each wrong guess generates a signal: you were wrong, adjust the dials. Each tiny adjustment requires a pass through the entire network. Doing this once for a complex model on a single powerful computer could take minutes. But it needs to see billions of examples, making quadrillions of adjustments, to become reliable. On a single machine, this process would span human lifetimes. The dream was stuck in quicksand. The assembly begins. The solution is breathtakingly bold: if one GPU isn't enough, use 10,000. Connect them not with standard cables, but with a neural system of their own, an ultra-high-speed, low-latency network fabric, like NVLink or InfiniBand, that allows them to share data almost as if they were parts of a single, colossal chip. This is the foundational act of building an AI supercomputer. The Cathedral of Silicon, the AI supercomputer materializes. It is not a sleek monolith but a cathedral of silicon and light. It fills a warehouse, endless rows of server racks, a symphony of blinking lights. The heat generated is so intense that it requires industrial-scale cooling, rivers of chilled water or even immersion tanks where the servers bathe in specialized fluid. This is a machine built for one divine purpose: calculation. The neural blueprint, software orchestrators, like PyTorch or TensorFlow, perform the delicate surgery. They take the giant neural network model, now called a foundation model, and slice it intelligently across the sea of GPUs. Some chips handle one layer of the network, others handle another. They all work in parallel, a choreography of synchronized thought. Feeding the beast, the data, the entire text of the internet, every public image, every known protein sequence, decades of scientific journals, streams into the system. This isn't just big data, it's the totality of human digital knowledge, the lifeblood required to create a general intelligence. The synchronized dance. This is the most critical, fragile part of the process. After processing a batch of data, each of the 10,000 GPUs has a slightly different idea of how to adjust the model's dials. They must instantly synchronize, share their findings and agree on a single, unified update for the entire network. The speed of this consensus, measured in terabits per second, determines whether the training is efficient or hopelessly bogged down. The network is the computer. Scale is everything. A paradigm-shattering law emerges, scaling law. Researchers discover that the capability of an AI model predictably improves as you increase three things in tandem: the size of the model, more parameters, the amount of training data, and the compute power used. More isn't just better, it unlocks emergent abilities, skills like reasoning, coding, or nuanced conversation that weren't explicitly taught but arose from scale. The breakthrough: after weeks of non-stop, planet-scale calculation, the training run completes. The noise settles. What emerges is a new entity, a foundation model. When prompted, it writes a sonnet in the style of Shakespeare, explains quantum physics in simple terms, or designs a valid protein for a new vaccine. The supercomputer's months of labor have crystallized into a brain that can now run on a much smaller machine, its intelligence distilled. The two giants, the landscape consolidates. On one side are the pioneers, OpenAI, Google DeepMind, Meta, who build their own private supercomputers to push the frontier of AI capability itself. On the other are the armories, AWS, Microsoft Azure, Google Cloud, who build these behemoths to rent their power, allowing thousands of companies and researchers to access this capability without building their own cathedral. The race for leadership: the story becomes a cyclical sprint. Every 12 to 18 months, a new generation of chips, more powerful, more efficient, is unveiled. A new supercomputer, 2x or 3x more powerful than the last, comes online. Each new exaflop of power unlocks the next generation of models, creating a self-reinforcing cycle of advancement. Leadership in AI is now directly tied to leadership in supercomputing. Beyond silicon, the next tool: the quest for efficiency breeds specialization. Companies design chips from the ground up for AI, Google's TPU, AWS Trainium, neuromorphic chips. These are not general-purpose armies but dedicated task forces, promising to do more thinking with less power, shaping the next evolution of the supercomputer's heart. The curious onlooker becomes the user, the power begins to diffuse. A climate scientist, using cloud-based supercomputing time, runs a hyper-detailed model of atmospheric chemistry to find new pathways for carbon capture. The supercomputer is no longer just for creating AI, it is the essential tool for the most complex problems in science, medicine, and engineering. The strategic resource: nations and boardrooms make a sobering realization. AI supercomputing is the modern equivalent of steel mills or oil fields. It is the foundational infrastructure of the 21st century, vital for economic leadership, military advantage, and scientific supremacy. It becomes a matter of geopolitics. The energy paradox, the Faustian bargain, the central conflict of our epoch, comes into stark relief. A single top-tier AI training run can consume more electricity than a small town uses in a year. The pursuit of godlike intelligence collides with the imperative of planetary sustainability. The race is now twofold, not just for more powerful compute, but for greener compute, driving revolutionary advances in nuclear fusion, advanced geothermal, and power-efficient chip design. The new landscape: our story concludes not with an end, but with a permanent transformation. AI supercomputers are the alchemical furnaces of our time. They ingest raw data, the digital ore of our world, and through a process of unimaginable scale and complexity, transmute it into a new form of capital, intelligence. This intelligence is now embedded in every field, from art to zoology, reshaping the very fabric of human capability. The epic continues, faster than ever, as we learn to wield the power of the thinking machines we have built.